So my name is Elijah Gonzalez. I am an undergraduate researcher here at Rice University. And over the summer and into the fall, my project has been working on the phase problem in protein crystallography, and specifically we're interested in ab initio phase retrieval for high solvent content crystals. So if you attended Jeff's talk yesterday, this project is kind of the application of all the theory that he mentioned. So kind of the end of his presentation is more or less the point of departure for where we're going to start today. So normally when I give this talk, I give this to people who are not crystallographers and people who are not familiar with the phase problem. But seeing as everyone here has heard about the phase problem kind of ad nauseum throughout this workshop, I'm just going to go ahead and go very briefly through the introduction. So of course we know that protein structures can be determined from X-ray diffraction patterns, and we do this by having to solve the phase problem, where we take a protein and we recover this, this diffraction pattern, and then we want to go back to electron density. And we use something called a Fourier transform, but in order to do this Fourier transform, we need phases. And of course, most people don't know what the phase problem is by the first time I present it. But again, most of us should already know it by this point. The only reminder that I would pose is just to remind everyone that indeed electron density and diffraction patterns are related by a Fourier transform. If we have our experiment, we know that during diffraction, we're able to measure the intensities of light. These intensities are proportional to essentially the magnitudes of complex structure factors. But since these structure factors are indeed complex and we're only recording magnitudes, we're missing phases. And these phases are essentially encoding how much of our vector is real and how much of it is imaginary. And we know that we need to know that in order to perform the Fourier transform. And so our group is a group of crystallographers. We're not essentially trying to reinvent the wheel by any means. We're just trying to use phasing methods to see how this is going to apply to protein crystallography. And so what we might think about is experimental methods for how the phase problem is solved. And this kind of ties into Sabina's talk from yesterday. But we know that each of these experimental methods has their own difficulties, as any kind of phasing protocol has. There's difficulties inherent in anything. So for something like multiple isomorphous replacement, we know that we encounter difficulties sometimes of non-isomorphism between substituted crystals. For something like single or multiple anomalous dispersion, there's sometimes difficulty expressing selenomethionine substituted proteins within eukaryotic hosts, although we know that we could use sulfur atoms within cysteine residues and methionine residues. And then kind of for existing computational methods, and by this I mean any computational methods, 5 or 10 years ago, right? These generally require high resolution data or a relatively small protein. And so you can kind of see where I'm going here, right? What would we like to do? We'd like to be able to phase our protein ab initio. That is, we'd like to go directly from intensities, then back to electron density without needing to know what the prior structure looked like, and being able to do this for any protein of any reasonable size scale. And so yesterday, Jeff mentioned an algorithm called the iterative projection algorithm. And of course, we've seen many of them today. And just kind of thinking about what that looks like, right? We have some sort of constraint where we're projecting our object onto that constraint. And this is taken from Jeff's talk. So if you haven't seen Jeff's talk, I would highly recommend you go watch that. It was incredibly informative. And I cannot claim to understand this nearly as well as Jeff does, but this is just kind of my abridged version of it. So we have a constraint where we're projecting an object onto. If we have two constraints, we can iteratively project onto both constraints until we reach a solution that represents the intersection of these constraints. And for protein crystallography, this intersection is essentially going to be a solved electron density structure of our protein, right? And so what are these constraints, right? Well, again, remember from Jeff's talk that we have a magnitude constraint and a support constraint. This magnitude constraint is essentially us saying that we're going to have amplitudes for our model. And we're also going to have amplitudes that we observe during diffraction, right? Those amplitudes are going to be proportional to the intensities that we measure during diffraction. And so it should certainly be the case that the amplitudes that we recover for any model that we have should also agree with the amplitudes that we record during diffraction. Similarly, we have a support constraint. And this is essentially the idea of having a contrast between an image and a background. And for the case of the 2D smiley face, right, we have this two-dimensional smiley face against its blue background. And so we define the contrast between the smiley face and the background. But in the case of protein crystallography, what we might consider is the contrast between a protein and its solvent. And we might define that to be the support of it, right? And so here we are, we've now defined that this HIO, this hybrid input-output algorithm, which is an example of an iterative projection algorithm, we might say, okay, sweet, right? I can use this HIO then to solve phases for a protein. But we have to think about Rick's talk as well. In Rick's talk, he mentioned that the phase problem is underdetermined due to Friedel's law. And what does this mean, right? So you'll remember that we consider a crystal object, which is periodic, and we consider its diffraction pattern. And what we'd like to do is uniquely relate the two of these. We know that we have a density grid of n by n by n, so essentially n cubed. We have n cubed parameters that we're trying to solve for, and we have n cubed data that we record during diffraction. But the reality is that it's not really n cubed data, right? It's n cubed over 2 data because of Friedel symmetry. In other words, half of the data is unique, and so we can only use that half. So we have parameters and Friedel symmetry, and so clearly we're not going to be able to solve this system quite yet. And so then the question is that what do we do from here, right? How do we solve a protein phase problem? And so what I then would pose to you is then what would happen if we only have a protein that has 50% solvent content, right? So we know that when we're crystallizing proteins that they form these crystal lattices with a certain amount that is solvent and a certain amount that is protein. And so if we only have a crystal that has 50% solvent content, what that's going to mean is that we're only really interested in the densities of 50% of the crystal. And so then maybe we can relate the diffraction pattern uniquely to the crystal object. So we have again an n cubed grid, but now it's n cubed over 2 because we're only really trying to solve for n cubed over 2 parameters. We have n cubed data, and if, again, Friedel symmetry appears. And so now, in theory, there should be a unique relationship between the parameters and the data that we actually record. And so from there, we kind of arrive at the story so far when it comes to HIO algorithms. And of course, this is a non-exhaustive list of kind of all the scientific advances that have been made. Again, we're not really trying to reinvent the wheel. We are a team of crystallographers, and we are just happy to be along the ride for all these amazing phase talks. But what we're going to be interested in is the applications of these different phase retrieval methods. And so in particular, we're going to look at the DOM group. And in 2012, their publication showed that they could use this phase retrieval method that would work if the support was known ahead of time and it was a high solvent content crystal. And so this work really inspired Dr. He's group, and Dr. He is a collaborator with us from the University of Houston. And what Dr. He's group showed was that you did not need to know the support ahead of time. What you could do is define it during runtime in something very similar to a shrink wrap method that Jeff talked about earlier. And so that kind of leads us to where we are in terms of my project over the summer and during the fall, is then now applying this HIO phase retrieval method to protein crystallography, right? So what would we like to do? What are our goals? Well, we'd like to build a library of PDB deposited test cases, and we'd like to compare whether or not this HIO method can actually reproduce the electron density structures that were already deposited in the PDB. In other words, when somebody deposits their PDB structure, right, they're also depositing the diffraction patterns that were produced. And so what we'd like to do is then take those diffraction patterns, use them in the HIO, and then see if we can actually reproduce the structures, the known structures that were deposited. And that's what we're doing. We're comparing the results of previously resolved structures against HIO resolved structures. And eventually what we'd like to do is to improve the success rate of this HIO method to eventually apply to novel proteins. In other words, we're interested in testing the reliability and essentially the robustness of this method for protein crystallography. And if we know that it's robust, then we'd like to optimize it as well as we can. And so now I'd kind of like to walk you through what one iteration of the HIO looks like. We've already kind of seen it with Jeff yesterday, but this is just specifically for our lab, how we implement it. It's worthwhile to talk about the methods for it. So we're going to start off with random density, and we're going to assume it within the asymmetric unit of the protein, which you can then expand to the crystal, unit cell. And so with this random density, we're going to do a DFT into Fourier space, where we're going to have calculated phases and calculated amplitudes, right? And so you remember for any kind of iterative projection algorithm, right? Like we talked about earlier, we have this magnitude constraint and we have this, I'm forgetting the word for it. Support constraint, the support constraint, thank you, yeah. So we have a support constraint and a magnitude constraint. So for the magnitude constraint, what we're gonna think about is, hey, I have these calculated amplitudes. What we can do from there is say, okay, well, although these are calculated amplitudes, we can actually replace these with observed amplitudes, since the observed amplitudes are actually what we record during diffraction, right? So then now we're here, we can DFT back into real space, and this is where we're going to start thinking about the support constraint, right? So in order to have some sort of support, we're going to need to define it in the first place, and we're going to define it by calculating a weighted density map, and then saying, okay, well, based on this weighted density map, I probably have some idea of where the protein region is and then where the solvent region is. Once I partition the two of them, I can do a type of HIO solvent flattening in the solvent region, and I can do histogram matching in the protein region. And we'll talk a little bit more about that in depth in a little bit. And so since this is, of course, iterative, we're going through this for many, many, many iterations. And then eventually, we're going to stop and record the phases. And so now we're just going to talk about a little bit about how we're defining the support at runtime. And this will allow us to then partition, like I said, the two regions and actually do electron density modifications in both regions respectively. So defining a protein mask support, which will evolve in time, right, is going to be very similar to the shrink wrap method. Essentially, we're exploiting the fact that we know that density in the protein region is going to be greater than density in the solvent region. And so we're going to start off by calculating a weighted average electron density map. And that kind of analogy that I always use is imagine you had a leak in the ceiling and you had a blindfold on and you wanted to determine where this leak was, right? What you might do is carry a bucket around with you and walk around until you felt the bucket fill with liquid. If it filled with enough liquid, you would probably call that where the leak is. And if it was filling with no liquid, you wouldn't be around the leak. And so our leak is basically a protein, and the leak itself, like the liquid you're collecting, would be the density. And so in kind of scientific vocabulary, we're defining a density probe region of a particular size. We're also defining a cutoff value for this density. And then based on what kind of the density of each voxel and its nearest neighbors, we're then dividing the unit cell into a protein region and a solvent region based on this density cutoff value. And so, of course, this is the crude analogy, right? We're not really using a bucket. We're using some sort of basically a B factor you can think of, and we're smearing the density. We're not actually smearing the density itself. We're just smearing the density to calculate the map. And then we're leaving the real space density alone so that way it can keep on going through the loop. But this is essentially a B factor that we're smearing. And you'll remember from yesterday that this smearing is really good to help kind of not have these spiky density portions around where the protein is and where the solvent is. You'd like it to be a pretty smooth boundary. And so now that we have the protein and the solvent regions, what we can do is electron density modifications in both regions. So for the solvent region, right, let's go back to the bucket analogy. We have some sort of cutoff that we're assigning. And you'll remember from Jeff's talk that because this is HIO, we're not using traditional solvent flattening. We're using a kind of HIO solvent flattening where we have this feedback parameter. Here it's an epsilon, and yesterday's talk it was a beta. It's just a letter. Just this is the feedback parameter that we're going to use. And this feedback parameter is really good because it's going to kick us out of a local minimum if we encounter it. And that's great because compared to traditional solvent flattening, which may have, like you're doing an error reducing method, right? And you have this monotonic error decrease. Well, if you go into a local minimum, you're basically stuck there. But because this is HIO, we have the feedback parameter that we can use to kick us out. And so essentially what this is saying is that we're not actually assigning values outside of the mask to zero or outside of the protein mask to zero. We're just driving them to zero using this epsilon parameter. And as I already mentioned, this is really beneficial because it means that the HIO can easily overcome stagnation, which is basically just local minimum. So if we're actually in the protein region, right, what we can also do is use histogram matching, right? And so basically all this is saying is that, like, you know that a protein has a histogram that is pretty general, right? Like all proteins have a really similar histogram. And so if you have this reference histogram, right, and you take the density that you calculated from one of the iterations, let's say it looks like this is your initial histogram. This initial histogram does not look like what a protein histogram should look like. So you can perform histogram matching in order to make it look like something that you know a protein should look like, right? And so we're evolving over these iterations, right? This is an iterative procedure. We're doing this over many, many thousands and thousands of iterations, right? But eventually we're gonna have to know if we've reached a solution. And so since we are comparing our results with known results, you might say, okay, we'll just use phase error, right? You have phases, the PDB has phases, just compare them against one another. But the reality is we're going to want to do this for a novel case at some point. And so instead what we're going to use is an R value. And if you aren't familiar with what an R value is, it's essentially kind of recording the agreement or the error in agreement between the observed amplitudes and the calculated amplitudes. And of course they should agree. And we have to consider that we may be overfitting the data when we're doing this iterative loop. So what we're going to do is we're going to set a small portion of the data to not go through the HIO scheme. And we're going to compare and see whether or not those indices actually do agree with what we observed, even if they didn't enter the HIO scheme. And so generally R-free is going to be a more convincing proof of convergence. Sometimes you'll see people cite our work, but really as crystallographers, we're really interested in looking at the R-free values over time. So now let's look at the results, right? Let's look at what we are actually able to accomplish. So this is a movie generated by Mitch Miller in our lab. It is a really awesome movie to kind of show how the HIO evolves in time. In the top left, this is the unit cell where we see the ball and stick model of the protein. And we kind of show this here just to show you what the mask looks like as it evolves in time, essentially what the support looks like. And then this is the ball and stick model at kind of an atomic resolution. Later on, it'll populate with a mesh grid that's supposed to represent what the HIO density is actually showing over time. And then these are basically error plots. This is phase error and R-free error. And so I'll go ahead and let this movie play. What you'll want to pay attention to is how it's very poor at the beginning, right? We really aren't capturing any atomic level information until this steep drop in error. So I'll go ahead and let this play. So as I mentioned, crystallography literature is going to cite a steep drop in error as an R-free solution. And you'll notice that at first, it's a very, very, very bad map. And you'll notice as well that the mask isn't really quite accurate until it locks in. So even though we don't really have atomic level information yet, we do have a pretty good idea of what the support looks like. And that's going to be really good as we're evolving over the many iterations. But again, we're kind of stuck here. And you'll notice that the error does not decrease monotonically because this is not an error reducing method. This is HIO method. And we aren't cycling back and forth between error reducing and HIO. We're strictly using HIO for now. And so as we're continuously evolving in time, right, we're going to wait until we see this steep drop in the R-free value. Well, this is the phase error, but also the R-free. The two are correlated, in fact. And we're going to notice how it locks onto the atomic resolution, basically, of the protein. And it gets it almost exactly, right? And so as soon as it locks on, right, we're doing a really good job of calculating, here's the atomic coordinates of basically all the protein in its entirety in the unit cell. And so what we're noticing too is that as it's evolving over time, we also see this drop at the end. And this drop at the end is going to actually be traditional solvent flattening. And so this traditional solvent flattening is more similar to the error reducing method. We don't cycle forth between HIO and error reducing. We just use error reducing at the end. But you'll notice how really good this electron density mesh grid is for the protein. And so one thing that's important to note is that the iterations necessary for convergence are actually different from for protein to protein. And that makes sense. That may be something that's not obvious to people when they first hear this talk, but particularly people who are not familiar with crystallography. But this is just an example of a movie generated of how it looks over time. But of course, we're not always generating these movies. Sometimes what we'll do is we'll just look at the electron density grid after the fact, or we may look at the correlation coefficient. We're not monitoring over time. We're just checking at the end just to make sure that if we did have a steep R-free drop, we believe that to be a solved structure, and we can confirm that using a correlation coefficient or say a phase error. So then from there, we can look at something that is actually a plot that I've now generated. So this is the convergence for independent HIO trials. And they are independent trials because you'll remember at the beginning that we start off with a random number set. And so it may be the case that some random number sets are going to converge faster than others just because you got lucky, so to speak. And so we use multiple random number sets to really characterize whether or not the problem is or is not solvable for a protein using this particular method. And so again, traditional solvent flattening is implemented towards the end of each run, which is going to feel a lot like the error reducing method. So this is the plot for just one protein. This is one protein, 2I92 in space group P43212. But we're really interested in testing this for lots of proteins and seeing what the kind of trends show. So this is the plot for many proteins within space group P43212. I think my computer is lagging. Okay, here we go. So this is a plot for many proteins within space group P43212. And each plot that I've shown, each single line graph is only one of many independent calculations that were done. This is just one representative that I'm showing. Otherwise, if I were to show all of them that we did, it would be too cluttered on this graph. So we were able to find successful HIO convergence for 5 out of the 11 proteins that we tested. It's worth noting that each protein contained greater than 60% solvent content in their unit cell. And again, that each line is really only one of many, 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 many independent trial calculations. And so this is for one space group. We'd also like to see if this works really for any space group. And so we moved on to another space group. And here we found that we achieved successful HIO convergence for 2 out of 11 proteins that we tested, which this is not actually due to some difficulty in P212121. It actually has to do with the fact that we used quote unquote harder problems. So we were trying to test a hypothesis about the contrast with the protein and the solvent. And we were interested in looking at proteins that were crystallized in a solvent that had low electron density. And so we then thought, if this is low electron density solvent, maybe we can use a low solvent fraction as well, since we're really, we have good contrast, so maybe we can lower the solvent fraction, but it wasn't the case after all, or at least we didn't have conclusive results to show that it was the case. And so one thing that we began noticing as we did this over many different proteins was that there are certain input parameters that are very, very, very sensitive. And so what we'd also like to do is try messing with some of these input parameters. And so one of them that we messed with was solvent fraction. And essentially what solvent fraction, we say a delta solvent fraction because in the PDB, we know that it was deposited with some sort of recorded solvent fraction. But if you actually were to use the solvent fraction that is recorded in the PDB, you won't actually have HIO convergence. And so what we tested is then what is the range for solvent fractions that are different from the actual solvent fraction deposited? So what is this so-called delta solvent fraction that you have to use in order to get to solution convergence? And just in this one case, it happened to be 0.04 less than the actual solvent fraction that was deposited in the PDB. We aren't suggesting that 0.04 is some sort of magic number, but it is worth noting that nevertheless, solvent content is a very, very, very sensitive parameter. And as a consequence, it should be noted that seemingly unsolvable cases might be able to be solved through effective parameter tweaking. And so, of course, this is eventually going to lead us to what we'd like to do in the future, right? So we have shown that convergence to a solution is possible through the HIO method for proteins in multiple space groups. But what we'd really like to do is characterize the relationships between these input parameters and whether or not we're going to get convergence. And so the reason why we'd like to do this is because we want to eventually apply this HIO method to a novel unsolved protein. And if we're going to go there, we want to know what it means to do effective parameter tweaking. Should we be messing with solvent fraction? Should we change the Gaussian filter, right? We're interested in looking at the relationships of these input parameters and whether or not we can kind of squeeze out some convergence based on just effective parameter tweaking. And so some future directions would be to exploit non-crystallographic symmetry in order to lower the high solvent content requirement. And so what this would do is allow us to essentially reduce it so we don't have to use such high solvent content requirements. And what we can also do is consider the effect of solvent contrast, low electron density, when defining a support. We really did not have conclusive results. It was more so just a case for like 4 out of the 5 proteins that we tested. And it would be really great if we could define some sort of, definitive relationship between whether or not there's more HIO, like you have a higher success rate if you're solvent, if you have like more solvent contrast, basically. But that's essentially would be a future direction. And then finally would be to reduce the computational load by reading reflections in using an iterative weighting factor. In other words, this is very, very difficult for computers, especially just because it's just many iterations over time. And so if we can reduce the computational load, we want to make sure that we're characterizing this from a phase problem perspective and not just, it just so happens that, say, your protein has too many reflections for this to be feasible. And so we're thinking about ways to reduce that computational load as well. So just finally, as some acknowledgements, I'd like to thank Exfil. I was an intern for them over the summer. I had a lot of fun, and I've been working in the George Phillips lab now throughout the fall. And it's been a really fun time. I've learned a lot about phase retrieval. I knew nothing about crystallography before the summer. So this has been a very exciting project. But I would be happy to take any questions if anyone had any.